Hello, my name is Joost de Jong, and this is a pre-recorded presentation for the 2021 meeting for Society for Mathematical Psychology. Today we're going to talk about time perception. Time perception researchers typically dissociate between two types of timing, retrospective and prospective timing. In a typical retrospective paradigm, we'd ask participants to remember letters on the screen. And to the surprise of the participants, we ask how long the task lasted. In the prospective paradigm, we ask participants to remember letters on the screen and track how long the task lasts. So now, as the letters are presented, participants can form an estimate of how long the task lasted. A large meta-analysis by Block and colleagues shows that cognitive load differentially affects retrospective and prospective timing. In the retrospective paradigms, when cognitive load is increased, time estimates also increase. Block and colleagues account for this effect by assuming that retrospective timing is based on memory. So when load is increased, more events are encoded and remembered in memory, leading to longer time estimates. In contrast, in the prospective paradigm, when load is increased, time estimates decrease. Block and colleagues account for this effect by proposing that prospective timing is based on an internal clock mechanism. So when load is increased, less ticks are counted from the clock because the clock is not attended to, leading to shorter estimates. We model time perception with a recurrent neural network called the Legendre delay network. This network not only represents its current input, but also a window of time spanning the current moment up until some arbitrary moment in the past. The network represents this window with coefficients. These are represented with these little dots. These coefficients are coefficients on temporal basis functions. And so when we multiply these coefficients with their respective temporal basis functions, right here, and then we take their sum, we can see in this black line that the network does a fine job of representing not just its current input, but also a window of time. Let's see how this works in action. So as new inputs arrive to the network adjusts its coefficients, not just based on the input, but also based on its current state, maintaining a representation of the past. So we can nicely see that new inputs are encoded at the start of the window, and past inputs are maintained inside the window. If we want to model more complex tasks, we also need more complex inputs. So here we present a network with vectors. On the y-axis, we can see the vector activation, and we first present the orange, then the green, then the red, and then the purple vector. And we can see at this point in time, the network has a fair reconstruction of its past inputs. So how do we construct a time estimate from this representation? We propose that integrating the absolute value of these representations and then summing them together can give a fair estimate of time. This looks much like the retrospective case. But what happens if we know beforehand that we have to time the duration of the task? We propose that a good way to do this is to present a network with a self-sustained vector. So this is a temporal vector. We can see at the end of the interval that the network represents this interval fairly well, and we can get a good time estimate out of this. But if we model retrospective and prospective timing as essentially the same representational and computational process, how do we account for differences between them? It's important to note that the network represents the stimuli and this temporal vector by adding them together. So if we do mathematical summation of vectors, we can see that both the temporal vector and the stimulus vector can still be decoded from their sum quite well. That's represented in these dotted lines. However, if we do this in a neural network, our neural network naturally normalizes vectors. So this means that we now cannot perfectly decode the original vectors anymore. We can see that this summed vector is basically squeezed together, and that's due to neural saturation of our activation functions. So basically what happens, the two vectors interfere with each other. We propose that attentional gain is a good candidate mechanism for controlling this interference. So if we want to pay more attention to one of the vectors, we can multiply that vector with the neural gain. And we can see that as the gain is increased for this vector, so we pay more attention to this vector, there is more interference for the temporal vector. We propose that this interference nicely accounts for the interaction effect found in Block et al. So as more attention is paid to the stimuli in the retrospective case, time estimates also increase. However, in the prospective paradigm, as more attention is paid to the stimuli, prospective estimates go down, and this is because of interference. And note that this explanation is based on the assumption that retrospective and prospective timing rely on the same representational and computational principles, not on different ones. I'd really like to thank my collaborators, without whom this project wouldn't have been possible. Thank you for listening.